Hello and welcome to Sci Cam, the online science magazine show. I'm Michael Contario and joining me this week is Sonia Dunbar.
Hello!
Yeah, Sonia's going to be talking trees a bit later on, but I'm going to get us started this week with a beginner's guide to water. And just as a quick reminder, on YouTube and the Google Plus event page, there are spaces for you to comment. So if you've got any questions for either me or Sonia, do stick down in there and we'll try and get through those questions before the end of the show. So obviously water has been in the news recently with NASA's announcement. It seems that water is flowing on Mars. But I thought I'd kind of take a step back and just kind of look at water in general and explain just why it is that it's so weird. Because it doesn't quite behave like really anything else on the planet. It's got some special properties, and these are all down to kind of what some people would call the chemistry of it, but I'm a physicist, so I like to think about it as the physics of it a little bit, because when you get down to it, it's all about where the electrons are, the charge on those, and how they're arranged. So I think it's physics, really. And the thing is, what we have to do for that is we have to think of a thing called electronegativity. And that's a very long word, but quite a simple idea. So we know that in water, we've got, for every 2 atoms of hydrogen, we've got 1 of oxygen going in to make it up. That's what H2O means. And inside these atoms, we've got the positive nuclei in the center, and the electrons, which, depending on how deep you want to go into it, are either in orbitals around it or are kind of smudged with a probability distribution if you want to go into quantum physics. But we're going to ignore that for now. We're going to stay a bit more classical and just think about electrons existing in some area of space which is outside of this positive nucleus. And what electronegativity is the ability of an atom, when it's in a bond, to pull that like pairs of electrons towards itself. And it turns out that oxygen is one of the most electronegative elements there is. It really wants to pull those electrons towards itself. And with hydrogen, that is actually surprisingly electronegative, because hydrogen normally just has 1 proton in the nucleus and 1 electron. This means that the electron is in a low orbital quite close to the nucleus. The nucleus wants to pull on that quite strongly. So when you've got the hydrogens and the oxygens, you've got the oxygen, which is more electronegative, pulling the electrons in the bond closer to it, and the hydrogen just still holding on to those, not quite disassociating from it. So it's kind of, you might have learned about covalent and ionic bonds in chemistry. And covalent bonds are kind of where the atoms share the electrons, and ionic bonds are where one of the atoms basically takes the electrons, and all bonds are kind of in between that. But what we've got here is something that's very definitely still kind of covalent, but with lots of character heading towards ionic. It's a weird bond, basically. And what this means is that you've got the oxygen with all of the negative charge in it, because it's pulling these electrons closer to itself. So the oxygen seems to be slightly negative, and the hydrogens appear to be slightly positive. But if you kind of think about the way that they're arranged, you've not just got those electrons inside the bonds you've got to care about. The oxygen has another 4 electrons in its kind of outermost orbital that we also have to care about. And so normally we've got 4 pairs of electrons. Normally we'd expect them to just kind of arrange in kind of a tetrahedral shape. So if you imagine a pyramid with a triangular base and 3 triangular sides, you can imagine normally you think of the oxygen being the center of that pyramid. And at each corner, you'd have a pair of electrons. 2 of those would be free pairs of electrons, and 2 of those would be the pairs of electrons where they're being shared between the oxygen and the hydrogen. Because the oxygen's pulling so strongly, what you end up, and it's got these 2 free pairs of electrons, you actually get a slight deformation away from that. So that rather than having this nice normal bond, which is about, well, you actually get a couple of degrees bend away from that. And that is actually responsible for some of water's weird properties. In fact, the kind of like one that everyone knows is the fact that when water becomes ice, it expands. Normally you expect solids to, when things become solid, you expect them to contract, get smaller, which makes sense, or they're not moving around so much, the molecules or atoms inside them. and they're just all in a nice structure. But because of this weird bond angle, you don't actually get nice packing of the water. Normally, you have these nice tetrahedral shapes, they kind of all fit together nicely, and you get a nice tight packed structure. But with water, what you get is this kind of like weird crinkled hexagonal structure. And what that means is there's lots and lots of space inside the hexagon. And so in order for them to all kind of like all of the molecules to arrange themselves in the right way for this, then you get a slightly kind of bigger chemical. And that's why it expands. And actually this expansion kind of actually starts before it freezes. When it's getting down towards 0 atmospheric pressure, you actually get it all kind of readjusting and starting to go towards the shape. And so even though you're cooling, you're actually expanding for those last few degrees. So that's kind of why the shape is related to why ice is less dense than water. But the shape also is related to why it works and dissolves so many things. And water tends to get known sometimes as the universal solvent because it will dissolve so many things. And that's because, as I was saying before, the electronegativity of the oxygen means that it pulls all of the electrons towards it and ends up slightly negative, and the hydrogens are slightly positive. But because you've got this kind of like two sides of a triangle shape of the water molecule going on, that means that actually you've got all of the negative kind of like at the point, and all of the positive things are kind of slightly further down, which means that all the negative, if it was this shape, all the negative is more higher up, all the positive charges are lower down. So you've got two different ends of the molecule with two different charges on it, which you don't get in a lot of things. A lot of things, all the electrons might get sucked in towards the central atom. But because the rest of it is symmetrical, overall you've not got a side which is positively or negatively charged. And this is why water can dissolve so many things, like salts. Salts tend to be ionic compounds where you've got a positive atom and a negative atom. And what happens when they dissolve in water is the positive, I said atoms, that's really bad of me, positive and negative ions. Oh, I'd get in so much trouble if I didn't correct that. So we have positive and negative ions in the salt. Normally they're stuck tightly together in the solid, but when you have water, what will happen is the positive ions will end up being attracted to the oxygen, because that's slightly negative, and the negative ions will be attracted to the other side, towards the hydrogens, because they're slightly positively charged. And when you get this dissociation of the ions, they can then flow through the water with the water molecules. That is dissolving the salt. And that's what's happening on Mars. This is why it's so exciting, because we think that because water is so good at this and can dissolve so many things, then that's why we think it's probably crucial to life, because all of the proteins and things inside your body basically only work because they're going to be dissolved inside. It's not quite water, but inside the liquids inside you, of which a large proportion is water. So this is why we want to see if there is water on Mars, and not as a solid or a gas, as a liquid, because then that's when it can actually dissolve things. So that's why we're interested. And what's happened now is we've seen some places on Mars which looked like they changed, and it wasn't clear why. It looked like there might be some sort of water flow going on, but we weren't sure. But now what we've done is we detected, using a spectrographic technique, which I can't really go into here, that they're what we call hydrated salts. And so this is forms of the salts with effectively water molecules attached to them. It's not dissolved as such, it's kind of what you get almost before it dissolves. And the water molecules arrange themselves nicely because of these charges and the charges on the ions of the salt, and you get a nice structure. But that changes the chemical composition of it effectively, so it can be detected as being different from just dry salt. And what this means also is normally we expect on Mars water, because of low pressure, we expect water might be a gas. because as you go up, say, as you go up a mountain, you might have heard that you can't boil a cup of tea and make a cup of tea nicely up there because the water boils at a lower temperature. And that's because we've got lower pressure as you go up the mountain. Also why it's harder to breathe as you start getting up Everest. And so on Mars, it's got a less dense atmosphere, lower pressure in the atmosphere, so the water is more likely to boil at lower temperatures. But also Mars is just generally colder than Earth. It orbits the sun further out. And so what we've got there is it's more likely to freeze. So we might have ice there and steam, but no actual liquid water. But here we've got water being present and seemingly flowing and creating these features that we see in the Martian landscape. So that suggests that, yeah, there might actually be something. And the salts are key because the salts are what actually makes it so that we can have the liquid water. Salt, who knows, like from throwing salt on the roads, pardon me, we know that we throw salt on the roads in order to kind of melt ice, stop ice from forming until it gets really cold. But another thing is that also having dissolved salts in water will also help prevent it from boiling as well. We know that because we put salt sometimes in food in pans so that we can actually raise the temperature of the boiling water and cook the food faster. And that's all to do basically with how the water molecules can escape from the water to become a gas, or how they can freeze. And basically the salt dissolved in the water just makes it harder for the water to get to the surface of the ice to freeze on it. And you always get this interplay between the water freezing and the water melting. So if you've got salt getting in the way, you don't actually decrease the chance of the water molecule like falling off the ice and becoming liquid water again. But you do decrease the probability of it sticking to the ice, actually being able to get to the ice and stick. So you end up with overall more salt, less chance of basically going from water to ice. So when you're not changing the amount of ice to water, so you end up with more water. Basically, it doesn't freeze. And kind of the same thing happens when you're going to a gas as well, to steam. So this is why the salt is really important. We can detect the hydrated form of it, and it also gives an explanation for why we can even see these features that the flowing water is creating. So water, like something really common, but there's so much more to it, and that's even without getting into surface tension, the fact, which is why the water kind of like in a tube isn't flat. You'll kind of like see the edges going up at the edge of a container, and the water, it seems to stick to the sides, it sticks to windows, all that sort of thing. There's so much more to talk about water, but sadly that's kind of too much. There are books and books about this. I know I've had recommended to me, not had a chance to read yet, The Water Book by Alok Jha. So you might want to check that out if you want to know more about water. Over to you, Sonia.
Thank you. Yeah, water is incredibly important, and well, trees certainly use some of water's very special properties to pull the water all the way up their trunks to the tops. And I'm talking about a study that was published recently in Nature about how many trees there are on this planet. So plants, we know, they're really important to us humans. They produce all sorts of useful things. Food, chemicals that we use as drugs. They provide the oxygen that we need to breathe. Forests, as a collection of trees, are particularly important because then they actually support a vast array of the biodiversity of the world, and they help many of the major nutrient cycles, carbon and nitrogen. They're very good at sequestering carbon. They also provide timber for building and help control water quality. And these things are what we call ecosystem services. A single tree on its own can do some of the job, but you need a collection of trees in a forest to really provide the major benefits. So in this study, a large number of researchers, and the author list is quite extensive, I must say, from groups all across the world, North and South America, Europe, Africa, and Asia, set out to provide a much more accurate count of the number of trees in the world. Prior to this study, it was generally accepted that there were approximately 400 billion trees on the planet. You'd think that that's a pretty big number, really. That's not bad. This number was generated using satellite imagery. So what we've got is we've got pictures of the surface of the Earth where we've got forests taken by satellites, and then they're analyzed by various software that tries to infer tree density, so how many trees there are in any given area from that picture. This study increases the count of trees to 3.04 trillion. There are 10 times more trees than the previous study estimated. And to sort of put that in perspective, that means that there are 422 trees for each one of us. So that's a big difference in number. And the question is, how do they achieve such a different number? And the key here was that they actually combined the satellite imagery with on-the-ground actual counts of there is a tree there and there is another one. They performed an absolutely staggering 429,775 individual counts in areas on every continent except Antarctica. And from these counts, they managed to basically create a model for the 14 main biomes. And when I say biomes, I mean the different communities of plants and animals. So we're talking things like deserts are a biome, tropical rainforests are a biome. And because they had actual on-the-ground counts of trees, they were able to get a much more detailed idea of the total number of trees. It also showed that the number of trees varied according to the different habitat type. So it turns out that actually 43% of these 3 trillion trees are found in tropical and subtropical rainforests, whereas the great sort of boreal forests, the tundra forests full of conifers that stretch across much of North America and Russia, contain about 24% of the global total, but they actually have the highest number of trees per area, so they're packed in more tightly. Sadly, though, it's not all good news. Their research also looks at the factors that affect the tree total, and they found that in every habitat on the planet, human activity is having a detrimental effect. Forests are often pushed aside in the search for timber, space for agriculture, or just space for more settlements, really. And they looked at data that was collected over the last 12 years, and they suggest that on average, about 15 billion trees are cut down every year. And this effect is, well, actually, we've had a major effect over all of the environment for a very long time. Historical data suggests that actually the number of trees on the planet has halved since human civilization sort of became a major feature. It's also affected the trends that we see in ecosystems. So, for example, in general, warm temperatures and moist soil, they're the perfect conditions for trees to flourish in. However, in various biomes, so for example, flooded grasslands, they actually saw a negative relationship. So where you had the most optimal conditions, you didn't have the best count of trees for that environment. And they suggest that that's because that habitat, that perfect environment, has been mostly used for agriculture and human activity. And so the pristine natural environments are relegated to the slightly less optimal conditions in that area. So you might wonder why we care that there are 3 trillion trees. Why did we need to know that number? How does it help? The answer really is that information is always valuable. With a better estimate of tree population, it allows us to actually weigh up the ecological and economic losses and gains of any area we might want to cut down a lot better than if we don't know the full picture of what's there. Plants underpin most ecosystems, so it will help us work out what other creatures are around there, better biodiversity estimates in general. And obviously there are a lot more questions to ask. It would be useful to know where different species grew, because we've just talked about sort of the generic tree at this point. And different species have different roles and uses to us and to the environment, so they're not necessarily equivalent. depending on their uses. So overall, it is useful to know that there are indeed a lot of trees on the planet, but unfortunately we shouldn't take it as a sign that everything's okay. Without human influence, there could be nearly double the number of trees, and some species are much more threatened than others. A second study that came out yesterday in Nature Plants suggests that we remain largely unaware of the risks to plant populations. About 6% of plant species have been evaluated according to the IUCN Red List criteria. Now, if you're not familiar with the Red List, it evaluates whether a species is not of concern, starting to be threatened, whether it's endangered, critically endangered. You may be familiar with some prominent mammals on the Red List, things like tigers, pandas. People tend to be much more aware of them than the plants on the list. So the authors from an absolutely staggering 74 organizations and research institutes collaborated to assess the 1,478 species of cacti across the world. And they found that approximately 31%, about a third of species of cacti, are threatened at some level, with 99 species critically endangered. And that's the step before the plant is considered extinct in the wild. This percentage in their major group lands them as the 5th most threatened group. So ahead of them come cycads, so they're another plant that have been around since the dinosaurs, amphibians, poor old frogs, etc., corals, and conifers, our fir trees, and only those groups contain a higher proportion of threatened species. So you might wonder why cacti are so endangered. In keeping with the finding of threats to forests, it's unfortunately our fault again. Conversion of land to agriculture is the most widespread threat. It affects cactus species across much of the Americas. But one of the other main problems might surprise you. Is actually the illegal collection of these plants from the wild by what are termed as cactus rustlers. So cacti look very unique, and due to this unique appearance, there is a high demand for these iconic cacti for use in gardens and parks. And while some of the demand is met legally via plants that have been grown from seed by various suppliers, the authors have estimated in the paper that about 86% of the threatened species of cacti that are on display in parks and gardens have actually been taken from the wild. Since 1975, trade in these species has been illegal. They tried to help the situation. But some national parks have gone for more extreme measures to try and preserve their cacti. For example, the Saguaro National Park has taken to microchipping the cacti, much like you might do your family dog or cat, so that you can find them again if they go missing. That's exactly the use of the microchipping here, and it makes them less of a desirable target for these cactus rustlers because they can track the cactus, and that's not very helpful if you want to trade it away to some foreign country. The other thing that they can do is that if they have discovered a completely new species, generally they won't actually release the location of such cacti. They'll only be known by a few experts in the field that helped identify them. And that anonymity protects them from being acquired by collectors. But it's not all doom and gloom. Help is at hand for some plants, and it brings me to a cheerful note to end on, a plant breeding success here in the UK, and it's perhaps equivalent to if we managed to breed giant pandas here. Scientists at Bedgebury Pinetum successfully germinated about 100 seedlings of an incredibly rare plant known as the Japanese birch. It's listed as critically endangered on that IUCN Red List. There are just 21 trees in the wild of this plant. So the small population of trees in the wild then is incredibly vulnerable. And these 100 seedlings, they may not all grow to full trees, but they're certainly a start of a valuable resource. They intend to share them with other sort of arboretums, other tree sort of collections, botanical gardens, so that when they're spread out, there's much less chance of, say, disease or a natural disaster wiping out all known examples of that plant. And they're also intending to build a grove of these trees to provide a supply of seeds so that we might be able to help boost the wild populations. So to finish then, many congratulations to the team at Bedgebury, as well as their collaborators at the University of Oxford's Botanical Gardens, who led the expedition to collect over 1,000 seeds that led to this success.
Oh, thank you very much, Sonia. I wonder if what cactus collecting would have been a very popular hobby. It seems quite niche.
You'd think. Apparently, it was quite prevalent. It's less common these days because there are a lot more regulations, but it was quite prevalent in your typical time of cowboys and Indian films, and it was much more of a problem in places like Arizona, where these huge, the typical saguaro cactuses with like the two arms, were in demand because they were so iconic. And yeah, they had people deliberately sort of keeping an eye out for people stealing cacti.
Well, thank you very much. Thank you, Sonia, for your plant talk. Always good. Yeah, such a big thing. And and cacti as well. And the traditional way of getting water well trapped in the desert, I think, as well. So we sort of had a theme.
Indeed. Cheers with some water to your talk as well.
We sort of had a theme this month. We'll be back probably towards the end of October. We're hoping to put together a special edition on the Nobel Prizes and what we think about those. So until then, check all of our videos on our YouTube channel, the Sci Cam YouTube channel. And if you do have any questions about any of those or this one, do send them in. So thank you very much, and goodbye.
Goodbye.